Solve the system of equations using matrices. Use a calculator to write the matrix in reduced row echelon form. So the first thing that we're going to do is convert this system to a matrix. And to do that, we need to make sure that our x's are lined up in a column, our y's are all lined up in their column, and the z's are lined up in a column. And all of the constants need to be to the right of the equal sign. We'll have an x, y, z column in our matrix. The vertical augment bar represents the equal signs, and then we'll have a column for the constants to the right of that vertical bar. So for row 1, we use the coefficients of each of these variables, and we have 1, the coefficient of x, coefficient of y is -3, coefficient of z is 2, and then the constant is 6. For the second row, we have the coefficient on x being -2, coefficient of y is 1, coefficient of z is -3, and 10 is the constant to the right of the equal sign. For the third row, we have coefficient x is 1, coefficient y is -8, coefficient of z is 3, and then 28 is to the right of the equal sign. When we put this into our calculator, we're going to need to indicate how big it is, and the size of a matrix is given by the number of rows cross the number of columns, and in this case we have 3 rows and 4 columns, so we say this is a 3 by 4 matrix. In order to put this matrix into our calculator, we're going to access the matrix function. So we have to hit second to get our arrow in the cursor and access the blue features above all the buttons. So second matrix, and we go over to the right to the edit menu, and we're going to replace whatever was in matrix A with our new matrix, so we just hit number 1 or just enter when our cursor is next to number 1, which takes us into matrix A. Now we tell the calculator that it's a 3 by 4 matrix so that the calculator opens up a matrix of the appropriate size, and then we enter in our matrix row by row starting with the first row. So we have 1, -3, 2, and 6. It automatically wraps us around to the next row, and we have -2, 1, -3, and 10. Wrapping around to the third row, we end up with 1, -8, 3, and 28. To check our input, it's easier if we quit out of this matrix screen and pull the matrix to the home screen. So we'll do that by hitting second matrix again. This time we're going to access the names function in order to display the matrix that's in A. We hit enter in order to access matrix A, and then we hit enter again to display the matrix that we just plugged into A. And it's easier to verify our calculator input when we can see the complete matrix here on the home screen. Another benefit of having it on the home screen is that it's automatically now stored in the answer variable, which is easier to access than having to go second matrix names A. Now we want to operate on this matrix, so we're going to put matrix A in reduced row echelon form, but in our calculator we can also just say RREF of the matrix that's stored in the answer variable. In order to get the reduced row echelon function, we're going to go to matrix again. This is where all of our matrix operators are stored in our calculator. So we're now going to go over to math. The math menu contains the matrix operators, and we're going to go to the end of the list until we see RREF. So we select reduced row echelon form, and then we're going to say reduced row echelon form of the matrix that's stored in the answer variable and close that up. So we hit enter, and the calculator returns a matrix that looks a little strange. In order to clean it up a little bit, the first thing I'm going to do is hit the math button and turn all these decimals into fractions. So I'm going to select feature 1 to run the matrix through the fraction feature, and it cleans up my matrix a little bit, makes it easier to see. So let's copy down what we have here. We asked our calculator for a matrix in reduced row echelon form, and this is what it gives to us. It is still in reduced row echelon form though, because it has ones along the main diagonal as far as we can get it, and then zeros above and below those ones. And when our reduced row echelon form looks like this with a row of zeros along the bottom, this is an indicator that we have infinitely many solutions. And this is a scenario that comes about when we have 3 planes that intersect in a line. There would be infinitely many ordered triples that are on all 3 planes at the same time. So while there are infinitely many solutions, now we need to indicate where those solutions lie. And in order to do that, we need to return to the system of equations turning all these rows back into equations. So our first row is going to be x plus 7/5 z is equal to negative 36 over 5. Our second row is going to be 0 is the coefficient of x, 1 is the coefficient of y, and negative 1/5 is the coefficient on z. This is going to be equal to negative 22 over 5. And the row of zeros does not need to be written down. Since it translates to 0 is equal to 0, that row does not contribute to the way that we express our answer. Once we've returned to the system, the next thing that we want to do is solve for x and y in terms of the variable z. Notice we could easily subtract 7/5 z from both sides and add 1/5 z to both sides to solve for both x and y in these equations. So x will be equal to negative 7/5 z minus 36 over 5, and y will be equal to positive 1/5 z after I add that to both sides minus 22 over 5. And then we want to use set builder notation to write this infinite solution set, which is to say where the ordered triples are that put us on that line. And so our solution set is going to be the set of all ordered triples x, y, and z. Vertical bar means such that. And the criteria that need to be met are that x and y are calculated in this way. Given a value of z, we would plug that z into this equation to get the corresponding x value to determine what x would need to be in order to put us onto that line. Given a value of z, we would plug that quantity into this y equation to determine what y would need to be in order to put us onto that line. And z is the quantity that takes on any real number. So what this means is that we pick a real number for z, we plug that into our equations for x and y, and what we get from that is an ordered triple that is on the line considered to be the solution to this system of equations. So this is one way to express that infinite solution set. A second way that we can write this infinite solution set is just by writing one large ordered triple. An ordered triple would be of the form x, y, and z. So what we could do here is say, given some value of z, x would need to be negative 7/5 z minus 36 over 5. And we don't have to say x is equal to because this equation is in the x position. And the y value would be calculated by looking at 1/5 z minus 22 over 5. And again, we don't have to say y is equal to because this equation is in the y position. So z roams through the real numbers, and then we calculate the x and the y values using these equations to ensure that our ordered triple is a point that's on that intersection line. So this is another way that we could write that infinite solution set.